A geographic information system is a computer system designed to capture, store, manipulate, analyze, manage, and present all types of geographical data. The acronym GIS is sometimes used for Geographical Information Science or Geospatial Information Studies to refer to the academic discipline or career of working with geographic information systems, and is a large domain within the broader academic discipline of Geoinformatics. GIS can be thought of as a system that provides spatial data entry, management, retrieval, analysis, and visualization functions. The implementation of a GIS is often driven by jurisdictional, purpose, or application requirements. Generally, a GIS implementation may be custom designed for an organization. Hence, a GIS deployment developed for an application, jurisdiction, enterprise, or purpose may not be necessarily interoperable or compatible with a GIS that has been developed for some other application, jurisdiction, enterprise, or purpose. What goes beyond a GIS is a spatial data infrastructure, a concept that has no such restrictive boundaries. In a general sense, the term describes any information system that integrates, stores, edits, analyzes, shares, and displays geographic information for informing decision-making. GIS applications are tools that allow users to create interactive queries, analyze spatial information, edit data in maps, and present the results of all these operations. Geographic information science is the science underlying geographic concepts, applications, and systems. The first known use of the term geographic information system was by Roger Tomlinson in the year 1968 in his paper A Geographic Information System for Regional Planning. Tomlinson is also acknowledged as the father of GIS. Applications. GIS is a relatively broad term that can refer to a number of different technologies, processes, and methods. It is attached to many operations and has many applications related to engineering, planning, management, transport logistics, insurance, telecommunications, and business. For that reason, GIS and location intelligence applications can be the foundation for many location-enabled services that rely on analysis, visualization and dissemination of results for collaborative decision-making. GIS provides a technologically strong platform to every kind of location-based business personnels to update data geographically without wasting time to visit the field and update in database manually. GIS, when integrated with other powerful enterprise solutions like SAP, helps creating powerful decision support system at enterprise level. History of development. One of the first applications of spatial analysis in epidemiology is the 1832 Rapport sur la marche et les efforts du Cola copyright Ra dans Paris et l'Adar copyright Parlement de la Seine. The French geographer Charles Picquet represented the 48 districts of the city of Paris by half-tone color gradient according to the percentage of deaths by cholera per 1,000 inhabitants. In 1854 John Snow depicted a cholera outbreak in London using points to represent the locations of some individual cases, possibly the earliest use of a geographic methodology in epidemiology. His study of the distribution of cholera led to the source of the disease, a contaminated water pump. While the basic elements of topography and theme existed previously in cartography, the John Snow map was unique, using cartographic methods not only to depict but also to analyze clusters of geographically dependent phenomena. The earlier 20th century saw the development of photosincography, which allowed maps to be split into layers, for example one layer for vegetation and another for water. This was particularly used for printing contours. Drawing these was a labor-intensive task, but having them on a separate layer meant they could be worked on without the other layers to confuse the draftsman. This work was originally drawn on glass plates, but later plastic film was introduced, with the advantages of being lighter, using less storage space and being less brittle, among others. When all the layers were finished, they were combined into one image using a large process camera. Once color printing came in, the layers idea was also used for creating separate printing plates for each color. While the use of layers much later became one of the main typical features of a contemporary GIS, the photographic process just described is not considered to be a GIS in itself, as the maps were just images with no database to link them to. Computer hardware development spurred by nuclear weapon research led to general-purpose computer mapping applications by the early 1960s. The year 1960 saw the development of the world's first true operational GIS in Ottawa, Ontario, Canada by the Federal Department of Forestry and Rural Development. Developed by Dr. Roger Tomlinson, it was called the Canada Geographic Information System, CGIS, and was used to store, analyze, and manipulate data collected for the Canada Land Inventory, an effort to determine the land capability for rural Canada by mapping information about soils, agriculture, recreation, wildlife, waterfowl, forestry and land use at a scale of 1:50,000. A rating classification factor was also added to permit analysis. CGIS was an improvement over computer mapping applications as it provided capabilities for overlay, measurement, and digitizing scanning. It supported a national coordinate system that spanned the continent, coded lines as arcs having a true embedded topology, and it stored the attribute and locational information in separate files. As a result of this, Tomlinson has become known as the father of GIS, particularly for his use of overlays in promoting the spatial analysis of convergent geographic data. CGIS lasted into the 1990s and built a large digital land resource database in Canada. It was developed as a mainframe-based system in support of federal and provincial resource planning and management. Its strength was continent-wide analysis of complex datasets. The CGIS was never available commercially. In 1964, Howard T. Fisher formed the Laboratory for Computer Graphics and Spatial Analysis at the Harvard Graduate School of Design, where a number of important theoretical concepts in spatial data handling were developed, and which by the 1970s had distributed seminal software code and systems, such as SYMAP, GRID, and Odyssey that served as sources for subsequent commercial development to universities, research centers and corporations worldwide. By the early 1980s, M&S Computing along with Bentley Systems Incorporated for the CADA platform, Environmental Systems Research Institute, CORISA, Computer-Aided Resource Information System, MapInfo Corporation and IDASA, Earth Resource Data Analysis System, emerged as commercial vendors of GIS software, successfully incorporating many of the CGIS features, combining the first-generation approach to separation of spatial and attributes information with a second-generation approach to organizing attribute data into database structures. In parallel, the development of two public domain systems began in the late 1970s and earlier 1980s. In 1986, Mapping Display and Analysis System, the first desktop GIS product, emerged for the DOS operating system. This was renamed in 1990 to MapInfo for Windows when it was ported to the Microsoft Windows platform. This began the process of moving GIS from the research department into the business environment. By the end of the 20th century, the rapid growth in various systems had been consolidated and standardized on relatively few platforms, and users were beginning to explore viewing GIS data over the Internet, requiring data format and transfer standards. More recently, a growing number of free, open-source GIS packages run on a range of operating systems and can be customized to perform specific tasks. Increasingly, geospatial data and mapping applications are being made available via the World Wide Web. Several authoritative articles on the history of GIS have been published. GIS Techniques and Technology. Modern GIS technologies use digital information, for which various digitized data creation methods are used. The most common method of data creation is digitization, where a hard copy map or survey plan is transferred into a digital medium through the use of a CAD program, and georeferencing capabilities. With the wide availability of auto-rectified imagery, heads-up digitizing is becoming the main avenue through which geographic data is extracted. Heads-up digitizing involves the tracing of geographic data directly on top of the aerial imagery instead of by the traditional method of tracing the geographic form on a separate digitizing tablet. Relating information from different sources, GIS uses spatiotemporal location as the key index variable for all other information. Just as a relational database containing text or numbers can relate many different tables using common key index variables, GIS can relate unrelated information by using location as the key index variable. The key is the location and/or extent in space-time. Any variable that can be located spatially, and increasingly also temporally, can be referenced using a GIS. Locations or extents in Earth's spatial Eurotime may be recorded as dates times of occurrence, and X, Y, and Z coordinates representing longitude, latitude, and elevation, respectively. These GIS coordinates may represent other quantified systems of temporospatial reference. Units applied to recorded temporal spatial data can vary widely, but all Earth-based spatial Eurotemporal location and extent references should, ideally, be relatable to one another and ultimately to a real physical location or extent in spatial Eurotime. Related by accurate spatial information, an incredible variety of real-world and projected past or future data can be analyzed, interpreted and represented to facilitate education and decision-making. This key characteristic of GIS has begun to open new avenues of scientific inquiry into behaviors and patterns of previously considered unrelated real-world information. GIS uncertainties. GIS accuracy depends upon source data, and how it is encoded to be data referenced. Land surveyors have been able to provide a high level of positional accuracy utilizing the GPS-derived positions. High-resolution digital terrain and aerial imagery. Powerful computers and web technology are changing the quality, utility, and expectations of GIS to serve society on a grand scale, but nevertheless there are other source data that have an impact on overall GIS accuracy like paper maps, though these may be of limited use in achieving the desired accuracy since the aging of maps affects their dimensional stability. In developing a digital topographic database for a GIS, topographical maps are the main source, and aerial photography and satellite images are extra sources for collecting data and identifying attributes which can be mapped in layers over a location facsimile of scale. The scale of a map and geographical rendering area representation type are very important aspects since the information content depends mainly on the scale set and resulting locatability of the map's representations. In order to digitize a map, the map has to be checked within theoretical dimensions, then scanned into a raster format, and resulting raster data has to be given a theoretical dimension by a rubber sheeting warping technology process. A quantitative analysis of maps brings accuracy issues into focus. The electronic and other equipment used to make measurements for GIS is far more precise than the machines of conventional map analysis. All geographical data are inherently inaccurate, and these inaccuracies will propagate through GIS operations in ways that are difficult to predict. Data representation. GIS data represents real objects with digital data determining the mix. Real objects can be divided into two abstractions, discrete objects and continuous fields. Traditionally, there are two broad methods used to store data in a GIS for both kinds of abstractions: mapping references, raster images, and vector. Points, lines, and polygons are the stuff of mapped location attribute references. A new hybrid method of storing data is that of identifying point clouds, which combine three-dimensional points with RGB information at each point, returning a 3D color image. GIS thematic maps then are becoming more and more realistically visually descriptive of what they set out to show or determine. Data capture. Data capture entering information into the Sistema consumes much of the time of GIS practitioners. There are a variety of methods used to enter data into a GIS where it is stored in a digital format. Existing data printed on paper or PET film maps can be digitized or scanned to produce digital data. A digitizer produces vector data as an operator traces points, lines, and polygon boundaries from a map. Scanning a map results in raster data that could be further processed to produce vector data. Survey data can be directly entered into a GIS from digital data collection systems on survey instruments using a technique called coordinate geometry. Positions from a global navigation satellite system like Global Positioning System can also be collected and then imported into a GIS. A current trend in data collection gives users the ability to utilize field computers with the ability to edit live data using wireless connections or disconnected editing sessions. This has been enhanced by the availability of low-cost mapping-grade GPS units with decimeter accuracy in real time. This eliminates the need to post-process, import, and update the data in the office after fieldwork has been collected. This includes the ability to incorporate positions collected using a laser rangefinder. New technologies also allow users to create maps as well as analysis directly in the field, making projects more efficient and mapping more accurate. Remotely sensed data also plays an important role in data collection and consists of sensors attached to a platform. Sensors include cameras, digital scanners and LiDAR, while platforms usually consist of aircraft and satellites. Recently, with the development of miniature UAVs, aerial data collection is becoming possible at much lower costs, and on a more frequent basis. For example, the Aryan Scout was used to map a 50-acre area with a ground sample distance of 1 inch in only 12 minutes. The majority of digital data currently comes from photo interpretation of aerial photographs. Soft copy workstations are used to digitize features directly from stereo pairs of digital photographs. These systems allow data to be captured in 2 and 3 dimensions, with elevations measured directly from a stereo pair using principles of photogrammetry. Analog aerial photos must be scanned before being entered into a soft copy system. For high-quality digital cameras, this step is skipped. Satellite remote sensing provides another important source of spatial data. Here, satellites use different sensor packages to passively measure the reflectance from parts of the electromagnetic spectrum or radio waves that were sent out from an active sensor such as radar. Remote sensing collects raster data that can be further processed using different bands to identify objects and classes of interest, such as land cover. When data is captured, the user should consider if the data should be captured with either a relative accuracy or absolute accuracy, since this could not only influence how information will be interpreted but also the cost of data capture. After entering data into a GIS, the data usually requires editing, to remove errors, or further processing. For vector data, it must be made topologically correct before it can be used for some advanced analysis. For example, in a road network, lines must connect with nodes at an intersection. Errors such as undershoots and overshoots must also be removed. For scanned maps, blemishes on the source map may need to be removed from the resulting raster. For example, a fleck of dirt might connect 2 lines that should not be connected. Raster to vector translation, data restructuring can be performed by a GIS to convert data into different formats. For example, a GIS may be used to convert a satellite image map to a vector structure by generating lines around all cells with the same classification, while determining the cell spatial relationships, such as adjacency or inclusion. More advanced data processing can occur with image processing, a technique developed in the late 1960s by NASA and the private sector to provide contrast enhancement, false color rendering and a variety of other techniques including use of 2-dimensional Fourier transforms. Since digital data is collected and stored in various ways, the 2 data sources may not be entirely compatible. So a GIS must be able to convert geographic data from one structure to another. Projections, coordinate systems, and registration. The Earth can be represented by various models, each of which may provide a different set of coordinates for any given point on the Earth's surface. The simplest model is to assume the Earth is a perfect sphere. As more measurements of the Earth have accumulated, the models of the Earth have become more sophisticated and more accurate. In fact, there are models called datums that apply to different areas of the Earth to provide increased accuracy, like 83 Namibian dollars for U.S. measurements, and the World Geodetic System for worldwide measurements. Spatial analysis with GIS. GIS spatial analysis is a rapidly changing field, and GIS packages are increasingly including analytical tools as standard built-in facilities, as optional toolsets, as add-ins or analysts. In many instances these are provided by the original software suppliers, whilst in other cases facilities have been developed and are provided by third parties. Furthermore, many products offer software development kits, programming languages and language support, scripting facilities and/or special interfaces for developing one's own analytical tools or variants. The website Geospatial Analysis and associated book attempt to provide a reasonably comprehensive guide to the subject. The increased availability has created a new dimension to business intelligence termed spatial intelligence, which, when openly delivered via intranet, democratizes access to geographic and social network data. Geospatial intelligence, based on GIS spatial analysis, has also become a key element for security. GIS as a whole can be described as conversion to a vectorial representation or to any other digitization process. Slope and aspect. Slope can be defined as the steepness or gradient of a unit of terrain, usually measured as an angle in degrees or as a percentage. Aspect can be defined as the direction in which a unit of terrain faces. Aspect is usually expressed in degrees from north. Slope, aspect, and surface curvature in terrain analysis are all derived from neighborhood operations using elevation values of a cell's adjacent neighbors. Slope is a function of resolution, and the spatial resolution used to calculate slope and aspect should always be specified. Authors such as Skidmore, Jones and Zoll and Liu have compared techniques for calculating slope and aspect. The following method can be used to derive slope and aspect. The elevation at a point or unit of terrain will have perpendicular tangents passing through the point, in an east-west and north-south direction. These two tangents give two components, AZAX and AZAY, which then be used to determine the overall direction of slope, and the aspect of the slope. The gradient is defined as a vector quantity with components equal to the partial derivatives of the surface in the x and y directions. The calculation of the overall 3x3 grid slope S and aspect A for methods that determine east-west and north-south component use the following formulas respectively. Zoll and Liu describe another algorithm for calculating aspect, as follows. Data analysis. It is difficult to relate wetlands maps to rainfall amounts recorded at different points such as airports, television stations, and schools. A GIS, however, can be used to depict 2- and 3-dimensional characteristics of the Earth's surface, subsurface, and atmosphere from information points. For example, a GIS can quickly generate a map with isopleth or contour lines that indicate differing amounts of rainfall. Such a map can be thought of as a rainfall contour map. Many sophisticated methods can estimate the characteristics of surfaces from a limited number of point measurements. A 2-dimensional contour map created from the surface modeling of rainfall point measurements may be overlaid and analyzed with any other map in a GIS covering the same area. This GIS-derived map can then provide additional information, such as the viability of water power potential as a renewable energy source. Similarly, GIS can be used to compare other renewable energy resources to find the best geographic potential for a region. Additionally, from a series of 3-dimensional points, or digital elevation model, isopleth lines representing elevation contours can be generated, along with slope analysis, shaded relief, and other elevation products. Watersheds can be easily defined for any given reach, by computing all of the areas contiguous and uphill from any given point of interest. Similarly, an expected thalweg of where surface water would want to travel in intermittent and permanent streams can be computed from elevation data in the GIS. Topological modeling. A GIS can recognize and analyze the spatial relationships that exist within digitally stored spatial data. These topological relationships allow complex spatial modeling and analysis to be performed. Topological relationships between geometric entities traditionally include adjacency, containment, and proximity. Geometric networks. Geometric networks are linear networks of objects that can be used to represent interconnected features, and to perform special spatial analysis on them. A geometric network is composed of edges, which are connected at junction points, similar to graphs in mathematics and computer science. Just like graphs, networks can have weight and flow assigned to its edges, which can be used to represent various interconnected features more accurately. Geometric networks are often used to model road networks and public utility networks, such as electric, gas, and water networks. Network modeling is also commonly employed in transportation planning, hydrology modeling, and infrastructure modeling. Hydrological modeling. GIS hydrological models can provide a spatial element that other hydrological models lack, with the analysis of variables such as slope, aspect and watershed or catchment area. Terrain analysis is fundamental to hydrology, since water always flows down a slope. As basic terrain analysis of a digital elevation model involves calculation of slope and aspect, DEMs are very useful for hydrological analysis. Slope and aspect can then be used to determine direction of surface runoff, and hence flow accumulation for the formation of streams, rivers and lakes. Areas of divergent flow can also give a clear indication of the boundaries of a catchment. Once a flow direction and accumulation matrix has been created, queries can be performed that show contributing or dispersal areas at a certain point. More detail can be added to the model, such as terrain roughness, vegetation types and soil types, which can influence infiltration and evapotranspiration rates, and hence influencing surface flow. One of the main uses of hydrological modeling is in environmental contamination research. Cartographic modeling. The term cartographic modeling was probably coined by Dana Tomlin in his PhD dissertation and later in his book, which is the term in the title. Cartographic modeling refers to a process where several thematic layers of the same area are produced, processed, and analyzed. Tomlin used raster layers, but the overlay method can be used more generally. Operations on map layers can be combined into algorithms, and eventually into simulation or optimization models. Map overlay. The combination of several spatial data sets creates a new output vector data set, visually similar to stacking several maps of the same region. These overlays are similar to mathematical Venn diagram overlays. A union overlay combines the geographic features and attribute tables of both inputs into a single new output. An intersect overlay defines the area where both inputs overlap and retains a set of attribute fields for each. A symmetric difference overlay defines an output area that includes the total area of both inputs except for the overlapping area. Data extraction is a GIS process similar to vector overlay, though it can be used in either vector or raster data analysis. Rather than combining the properties and features of both datasets, data extraction involves using a clip, or mask to extract the features of one dataset that fall within the spatial extent of another dataset. In raster data analysis, the overlay of datasets is accomplished through a process known as local operation on multiple rasters, or map algebra, through a function that combines the values of each raster's matrix. This function may weigh some inputs more than others through use of an index model that reflects the influence of various factors upon a geographic phenomenon. Geostatistics. Geostatistics is a branch of statistics that deals with field data, spatial data with a continuous index. It provides methods to model spatial correlation, and predict values at arbitrary locations. When phenomena are measured, the observation methods dictate the accuracy of any subsequent analysis. Due to the nature of the data, a constant or dynamic degree of precision is always lost in the measurement. This loss of precision is determined from the scale and distribution of the data collection. To determine the statistical relevance of the analysis, an average is determined so that points outside of any immediate measurement can be included to determine their predicted behavior. This is due to the limitations of the applied statistic and data collection methods, and interpolation is required to predict the behavior of particles, points, and locations that are not directly measurable. Interpolation is the process by which a surface is created, usually a raster data set, through the input of data collected at a number of sample points. There are several forms of interpolation, each which treats the data differently, depending on the properties of the data set. In comparing interpolation methods, the first consideration should be whether or not the source data will change. Next is whether the method is subjective, a human interpretation, or objective. Then there is the nature of transitions between points, are they abrupt or gradual? Finally, there is whether a method is global, or local where an algorithm is repeated for a small section of terrain. Interpolation is a justified measurement because of a spatial autocorrelation principle that recognizes that data collected at any position will have a great similarity to, or influence of those locations within its immediate vicinity. Digital elevation models, triangulated irregular networks, edge-finding algorithms, Thiessen polygons, Fourier analysis, moving averages, inverse distance weighting, kriging, spline, and trend surface analysis are all mathematical methods to produce interpolative data. Address geocoding. Geocoding is interpolating spatial locations from street addresses or any other spatially referenced data such as zip codes, parcel lots and address locations. A reference theme is required to geocode individual addresses, such as a road center line file with address ranges. The individual address locations have historically been interpolated, or estimated, by examining address ranges along a road segment. These are usually provided in the form of a table or database. The software will then place a dot approximately where that address belongs along the segment of center line. For example, an address point of 500 will be at the midpoint of a line segment that starts with address 1 and ends with address 1000. Geocoding can also be applied against actual parcel data, typically from municipal tax maps. In this case, the result of the geocoding will be an actually positioned space as opposed to an interpolated point. This approach is being increasingly used to provide more precise location information. Reverse geocoding. Reverse geocoding is the process of returning an estimated street address number as it relates to a given coordinate. For example, a user can click on a road center line theme and have information returned that reflects the estimated house number. This house number is interpolated from a range assigned to that road segment. If the user clicks at the midpoint of a segment that starts with address 1 and ends with 100, the returned value will be somewhere near 50. Note that reverse geocoding does not return actual addresses, only estimates of what should be there based on the predetermined range. Multi-criteria decision analysis, coupled with GIS, multi-criteria decision analysis methods support decision-makers in analyzing a set of alternative spatial solutions, such as the most likely ecological habitat for restoration, against multiple criteria, such as vegetation cover or roads. MCDA uses decision rules to aggregate the criteria, which allows the alternative solutions to be ranked or prioritized. GIS-MCDA may reduce costs and time involved in identifying potential restoration sites. Data output and cartography. Cartography is the design and production of maps, or visual representations of spatial data. The vast majority of modern cartography is done with the help of computers, usually using GIS, but production of quality cartography is also achieved by importing layers into a design program to refine it. Most GIS software gives the user substantial control over the appearance of the data. Cartographic work serves two major functions. First, it produces graphics on the screen or on paper that convey the results of analysis to the people who make decisions about resources. Wall maps and other graphics can be generated, allowing the viewer to visualize and thereby understand the results of analyses or simulations of potential events. Web map servers facilitate distribution of generated maps through web browsers using various implementations of web-based application programming interfaces. Second, other database information can be generated for further analysis or use. An example would be a list of all addresses within a near mile of a toxic spill. Graphic display techniques. Traditional maps are abstractions of the real world, a sampling of important elements portrayed on a sheet of paper with symbols to represent physical objects. People who use maps must interpret these symbols. Topographic maps show the shape of land surface with contour lines or with shaded relief. Today, graphic display techniques such as shading based on altitude in a GIS can make relationships among map elements visible, heightening one's ability to extract and analyze information. For example, two types of data were combined in a GIS to produce a perspective view of a portion of San Mateo County, California. The digital elevation model, consisting of surface elevations recorded on a 30-meter horizontal grid, shows high elevations as white and low elevation as black. The accompanying Landsat thematic mapper image shows a false color infrared image looking down at the same area in 30-meter pixels, or picture elements, for the same coordinate points, pixel by r pixel, as the elevation information. A GIS was used to register and combine the two images to render the three-dimensional perspective view looking down the San Andreas Fault, using the thematic mapper image pixels, but shaded using the elevation of the landforms. The GIS display depends on the viewing point of the observer and time of day of the display, to properly render the shadows created by the sun's rays at that latitude, longitude, and time of day. An archaeotrome is a new way of displaying spatial data. It is a thematic on a 3D map that is applied to a specific building or a part of a building. It is suited to the visual display of heat loss data. Spatial ETL. Spatial ETL tools provide the data processing functionality of traditional extract, transform, loader, ETL, software, but with a primary focus on the ability to manage spatial data. He provides GIS users with the ability to translate data between different standards and proprietary formats, whilst geometrically transforming the data en route. These tools can come in the form of add-ins to existing wider-purpose software such as Microsoft Excel. GIS data mining. GIS or spatial data mining is the application of data mining methods to spatial data. Data mining, which is the partially automated search for hidden patterns in large databases, offers great potential benefits for applied GIS procedure decision-making. Typical applications including environmental monitoring. A characteristic of such applications is that spatial correlation between data measurements require the use of specialized algorithms for more efficient data analysis. GIS developments. Many disciplines can benefit from GIS technology. An active GIS market has resulted in lower costs and continual improvements in the hardware and software components of GIS. These developments will, in turn, result in a much wider use of the technology throughout science, government, business, and industry, with applications including real estate, public health, crime mapping, national defense, sustainable development, natural resources, landscape architecture, archaeology, regional and community planning, transportation and logistics. GIS is also diverging into location-based services, which allows GPS-enabled mobile devices to display their location in relation to fixed assets, mobile assets, or to relay their position back to a central server for display or other processing. These services continue to develop with the increased integration of GPS functionality with increasingly powerful mobile electronics. Open Geospatial Consortium standards. The Open Geospatial Consortium is an international industry consortium of 384 companies, government agencies, universities, and individuals participating in a consensus process to develop publicly available geoprocessing specifications. Open interfaces and protocols defined by OpenGIS specifications support interoperable solutions that geo-enable the web, wireless and location-based services, and mainstream IT, and empower technology developers to make complex spatial information and services accessible and useful with all kinds of applications. Open Geospatial Consortium protocols include Web Map Service, and Web Feature Service. GIS products are broken down by THEA-OGC into two categories, based on how completely and accurately the software follows the OGC specifications. Compliant products are software products that comply to OGC OpenGIS specifications. When a product has been tested and certified as compliant through the OGC testing program, the product is automatically registered as compliant on this site. Implementing products are software products that implement OpenGIS specifications but have not yet passed a compliance test. Compliance tests are not available for all specifications. Developers can register their products as implementing draft or approved specifications, though OGC reserves the right to review and verify each entry. Web mapping. In recent years there has been an explosion of mapping applications on the web such as Google Maps and Bing Maps. These websites give the public access to huge amounts of geographic data. Some of them, like Google Maps and OpenLayers, expose an API that enable users to create custom applications. These toolkits commonly offer street maps, aerial satellite imagery, geocoding, searches, and routing functionality. Web mapping has also uncovered the potential of crowdsourcing geodata in projects like OpenStreetMap, which is a collaborative project to create a free editable map of the world. Global climate change, climate history program and prediction of its impact. Maps have traditionally been used to explore the Earth and to exploit its resources. GISA technology, as an expansion of cartographic science, has enhanced the efficiency and analytic power of traditional mapping. Now, as the scientific community recognizes the environmental consequences of anthropogenic activities influencing climate change, GISA technology is becoming an essential tool to understand the impacts of this change over time. GIS enables the combination of various sources of data with existing maps and up-to-date information from Earth observation satellites along with the outputs of climate change models. This can help in understanding the effects of climate change on complex natural systems. One of the classic examples of this is the study of Arctic ice melting. Adding the dimension of time, the condition of the Earth's surface, atmosphere, and subsurface can be examined by feeding satellite data into a GIS. GISA technology gives researchers the ability to examine the variations in Earth processes over days, months, and years. As an example, the changes in vegetation vigor through a growing season can be animated to determine when drought was most extensive in a particular region. The resulting graphic, known as a normalized vegetation index, represents a rough measure of plant health. Working with two variables over time would then allow researchers to detect regional differences in the lag between a decline in rainfall and its effect on vegetation. GISA technology and the availability of digital data on regional and global scales enable such analyses. The satellite sensor output used to generate a vegetation graphic is produced for example by the Advanced Very High Resolution Radiometer. This sensor system detects the amounts of energy reflected from the Earth's surface across various bands of the spectrum for surface areas of about 1 square kilometer. The satellite sensor produces images of a particular location on the Earth twice a day. AVHRR and more recently the Moderate Resolution Imaging Spectroradiometer are only two of many sensor systems used for Earth surface analysis. More sensors will follow, generating ever greater amounts of data. In addition to the integration of time and environmental studies, GIS is also being explored for its ability to track and model the progress of humans throughout their daily routines. A concrete example of progress in this area is the recent release of time-specific population data by the U.S. Census. In this dataset, the populations of cities are shown for daytime and evening hours, highlighting the pattern of concentration and dispersion generated by North American commuting patterns. The manipulation and generation of data required to produce this data would not have been possible without a GIS. Using models to project the data held by a GISA forward in time have enabled planners to test policy decisions using spatial decision support systems. Semantics, tools and technologies emerging from the W3C's data activity are proving useful for data integration problems in information systems. Correspondingly, such technologies have been proposed as a means to facilitate interoperability and data reuse among GISA applications and also to enable new analysis mechanisms. Ontologies are a key component of this semantic approach as they allow a formal, machine-readable specification of the concepts and relationships in a given domain. This in turn allows a GIS to focus on the intended meaning of data rather than its syntax or structure. For example, reasoning that a land cover type classified as deciduous needle-leaf trees in one dataset is a specialization or subset of land cover type forest in another more roughly classified dataset can help the GIS automatically merge the two datasets under the more general land cover classification. Tentative ontologies have been developed in areas related to GIS applications, for example the hydrology ontology developed by the Ordnance Survey in the United Kingdom and the suite ontologies developed by NASA's Jet Propulsion Laboratory. Also, Simpler ontologies and semantic metadata standards are being proposed by the W3C GeoIncubator group to represent geospatial data on the web. Geospatial is a standard developed by the Ordnance Survey, United States Geological Survey, Natural Resources Canada, Australia's Commonwealth Scientific and Industrial Research Organisation and others to support ontology creation and reasoning using well-understood OGC literals, topological relationships, RDF and the SPARQL database query protocols. Recent research results in this area can be seen in the International Conference on Geospatial Semantics and the Terra Cognita Directions to the Geospatial Semantic Web Workshop at the International Semantic Web Conference. Society. With the popularization of GIS in decision-making, scholars have begun to scrutinize the social implications of GIS. It has been argued that the production, distribution, utilization, and representation of geographic information are largely related with the social context. Other related topics include discussion on copyright, privacy, and censorship. A more optimistic social approach to GIS adoption is to use it as a tool for public participation. See also. References, footnotes. Some retrieved from Federal Geographic Data Committee, Notations, IGRS GIS Institute of Geoinformatics and Remote Sensing, further reading, Berry, J.K. Beyond Mapping, Concepts, Algorithms and Issues in GIS. Fort Collins, Colorado, GIS World Books. Bolstad, P. GIS Fundamentals, a first text on geographic information systems, 2nd edition. White Bear Lake, Minnesota, Ida Press, 543 pp. Burrow, P.A. and McDonnell, R.A. Principles of Geographical Information Systems. Oxford University Press, Oxford, 327 pp. Busey, G.D. and Robinson, D. Geographical Information Systems in Latin America, 1987-2010. A Preliminary Overview. Journal of Latin American Geography. 9, 3, 9-31. 2, Chang, K. Introduction to Geographic Information System, 4th edition. McGraw-Hill, ISBN 978-0071267588, De Smith M.J., Goodchild M.F., Longley P.A. Geospatial Analysis, A Comprehensive Guide to Principles, Techniques and Software Tools. Troubadour, UK. ISBN A978-1848761,582. Ilan Govan, KGIS, Fundamentals, Applications and Implementations, New India Publishing Agency, New Delhi 208 pp. Fu, P. and J. Sunday 2010. WebGIS, Principles and Applications. ESRI Press. Reedlands, C.A. ISBN 1-58948-245-X. Harvey, Francis, 2008, A Primer of GIS, Fundamental Geographic and Cartographic Concepts. The Guildford Press, 31 pp. Hayward, I., Cornelius, S., and Carver, S. An Introduction to Geographical Information Systems. Prentice Hall 3rd edition. Longley, P.A., Goodchild, M.F., Maguire, D.J. and Rind, D.W. Geographic Information Systems and Science. Chichester, Wiley. 2nd edition. Maguire, D.J., Goodchild M.F., Rind D.W. Geographic Information Systems, Principles, and Applications Longman Scientific and Technical, Harlow. Mallion v., Grigonis v., Palivia Alas v., Griffiths S. Geographic Information System, Old Principles with New Capabilities. Urban Design International 16, 1 Euro 6 doi, 10.1057/UDI. 2010.25 Minek, Brian E. Lawrence A. West, Junior Geographic Information Systems in Developing Countries, Issues in Data Collection, Implementation and Management. Journal of Global Information Management 9, 45 Euro 55 Ott, T. and Swayachi, F. Time Integrative GIS. Management and Analysis of Spatio-Temporal Data, Berlin/Heidelberg/New York, Springer. Sergeven G. Latitude and Longitude a Misunderstanding. Current Science 94, 568 Sergeven G. Customize and Empower. Geospatial Today 4, 40 43 Thurston, J., Poyker, T.K. and J. Patrick Moore. Integrated Geospatial Technologies, A Guide to GPS, GIS, and Data Logging. Hoboken, New Jersey, Wiley. Tomlinson, R.F., Thinking About GIS, Geographic Information System Planning for Managers. ESRI Press. 328 pp. Wise, SGIS Basics. London, Taylor and Francis. Werboys, Michael. Duckham, Matt. GIS, A Computing Perspective. Boca Raton, CRC Press. ISBN A0415283752. Wheatley, David and Gillings, Mark. Spatial Technology and Archaeology. The Archaeological Application of GIS. London, New York, Taylor and Francis. External links: Association of Geographic Information Laboratories for Europe, promoting academic teaching and research on GIS at the European level. Cartography and Geographic Information Society, Directions Magazine All Things Location, Federal Geographic Data Committee United States Federal Government Standards Agency. Geographic Information System Educational Website educational site with PDF lessons and videos to accompany free GIS software. GIS Development the Geospatial Communication Network, Land Surveyors United Geospatial Social Support Network Global Social Support Network featuring geospatial forums, instructional geospatial videos, industry news and support groups based on geolocation. GIS Lounge information site about GIS. GISKI Newsreader a searchable feed aggregator for a large collection of GIS news, mostly in English. GITA a Geospatial Information and Technology Association. International Cartographic Association, the world body for mapping and science professionals, National States Geographic Information Council, Open Forum on Participatory Geographic Information Systems and Technologies a global network of PGIS English-speaking practitioners and researchers with Spanish, Portuguese and French-speaking chapters. Open Geospatial Consortium, Incorporated. Open Source Geospatial Foundation, USGS GIS Poster a frequently cited, What is GIS Poster?